Yeah, first of all, thank you for the invitation. It's really a pleasure to come here to tell you guys a bit about the work that we do. And so I'm a new assistant professor at Lancaster University, and I'm in the process of setting up our lab. And just a little bit of background on myself. Zhang mentioned most of it. I did my undergrad study at Georgia Institute of Technology in chemical engineering, and I did my PhD study at the University of Toronto, also in chemical engineering. So I'm an engineer by training. Right? And the reason I'm here today is because the research that I do have a really direct translational aspects. So I want to meet with clinicians who can help us to take the product, the technology from our benchtop and apply directly to the patients. So the long-term objective or goal of our research is really to engineer, grow a functional human organ, functional human tissue. And this entire area has been around for nearly 2 decades. So roughly around more than a decade ago, Robert Langer, a professor from MIT, first showed this image to the world. And it really captured the imagination of the public. It made it seem like that these engineered human-grown organs or tissues are so close and within our reach. But clearly the reality is a bit different. It's a lot more complicated to do this. And today we don't have a tissue that's grown in the lab and can be implanted into a patient. The technology is just not there yet. It's not quite in the market. So then the question is, what is the challenges? What are the hurdles? So one of the major challenges that we're facing today in this area is tissue vascularization. So these blood vessel networks, they are so important. They're so prevalent in our body. They're a major part of almost every single organs in the body. And without these vasculature, which is to supply oxygen and nutrient deep into the tissue, we simply cannot grow a tissue that is large enough because the cells inside that tissue will eventually die. And then at the end, we just end up with this tissue that's shaped like a hollow shell with a thin layer of cells that are alive on the surfaces, which is not something that's desirable and transplantable. So the vascular system is clearly very complex. And then the question is, how can we reproduce this natural complexity in the lab? The natural growth of a blood vessel network has this fancy name called angiogenesis. But the only thing you need to know about this is that this is a process that is very slow and very difficult to control. So instead of relying on this natural growth of blood vessels, in our lab we thought, can we use an engineering technique to directly construct these blood vessel networks from the bottom up? Right? To do this, we thought, can we borrow the fabrication technique from the semiconductor industry, which has been used to make these microcircuitries, these very complex microcircuitries on a computer chip, but apply this technique to the fabrication of biomaterial to construct a bioscaffold that contains an intricate network of microchannels that can be populated with living cells to mimic the blood vessel network. So to do this, we developed this product called AngioChip. Now from this name, you can clearly see we're trying to merge these 2 different areas of studies. So what exactly is AngioChip? AngioChip is essentially just a scaffold that is made from a synthetic, biodegradable, and biocompatible polymer. This scaffold contains this really intricate microchannel network that are interconnected and perfusible through a single inlet and a single outlet, just like how we can produce a vasculature. And then we can see it on the interluminal surface of these channels with endothelial cells, which are the cells that make up the vascular barrier in a vessel. And then surrounding this vessel network, we can populate the scaffold with any type of parenchymal cells, such as the liver cells, cells from heart muscles, cells from skeletal muscles, or even cancer cells to derive a variety of organ systems. And just to show you how small these vessels are, here is an image of a tissue derived from this scaffold, and you can see the smallest vessel in that tissue is as small as the tip of this ball pen. Right? So in fact, these vessels have a diameter of around 100 micron, which is similar to the size of a single human hair. So they're quite small. And this is the bioreactor that we typically use to culture these artificial tissues. And you can see there's a tissue suspended in the middle is internal vasculature perfusible by perfusing this color dye through it for visual effects. Now we can zoom into this tissue to actually see what's going on inside. Inside the tissue, I said we have these vasculatures. To visualize these vasculatures, we stain the endothelial cells in this red dye. And you can see the endothelial cells covering on the inner luminous surface of these microchannels, forming that vascular barrier to mimic a blood vessel. And these cells can also branch out further into even smaller microvasculatures, capillaries. Now, once we have this vascular network, the second step of creating a living tissue is to then populate it with other parenchymal cells. So in this case, to create a functional heart muscle, we seeded human embryonic stem cell-derived cardiac muscle cells, called cardiomyocytes, inside the scaffold. And we culture these cells for a few days to allow the cells to integrate with each other. And once they're integrated, they can contract synchronously as a whole, as a single tissue. And you can see the entire tissue is contracting here. With each contraction, it bends the scaffold. And this tissue also displays this impulse propagation, essentially conducting electricity through the entire tissue construct. And then when we inject a drug, like epinephrine, which is adrenaline, through the internal vasculature of this tissue, we can accelerate the beating frequency of this tissue. Just like how it works in the body. When we inject adrenaline into our body, we get increased heart rate. Now, one important advantage of this technology is the vessel network that we can directly construct here are mechanically stable. This means we can surgically manipulate it to connect it to the circulation of a host using surgical procedure. So when we do the implantation, we get immediate blood perfusion through the vasculature of these implants. And to prove this, here we implanted our tissue on the rat tight-limbed in two different configurations. And you can see after the surgical procedure, when we release the clamp that was clamping the femoral artery, we get immediate blood perfusion through the vasculature of the implant. And we were able to leave the tissue in the rat for about 1 week. After 1 week, you can still visualize the vascular perfusion there, and the tissue were able to survive and get integrated with the host tissues. So now the question is, from here, where do we go, right, in the future? So there are two directions. One is scaling up, the other is scaling down. For clinical translational applications, right, using this type of tissue, implanting them into a patient, we need to scale the tissue up. The tissue we are making here, they're still quite small. They can literally fit on the top of your thumb. And that's too small to have any therapeutic potential for humans, right? So, at McMaster in my lab, so that will be the direction I will be focusing on, is figuring out a way how to scale up the production of these scaffolds so we can engineer a much larger, more complex vascular network that can support a larger tissues. Now, there's another direction, and that is scaling down. So these tissues, we can scale them down further to make them even smaller. By making them smaller, this means we use less cells. And by using less cells, we're reducing the cost of making each individual tissue. So this means we can make many of them. And this is particularly useful when you want to do drug testings, because you want to test many different drugs at different dosages. So that's what we have done. So far we have used cells from liver, cells from heart, or even cancer cells from tumor. We were able to grow them around this synthetic vasculature inside these small wells in the standard 96-well plate format. So we can have many tissues in there. And using this vasculature, we can even connect them together, link different organ systems together to study how different organs interact with each other. And so when we apply drug onto it, this means we can directly observe, for example, how a drug is metabolized by the liver and how the metabolite will be able to affect the heart muscle downstream or even cancer tumors downstream. So when you do drug testing in this type of multi-organ platform, you'll be able to better evaluate the effect of the drug and potentially even capture certain side effects. before you move a drug to human clinical trials. So based on work like this, in 2014, me and my supervisor co-founded a startup company called Taro Biosystem, which specializes in manufacturing these hard muscle tissues that are also can be situated inside these multi-well plate. And when we apply drug onto these tissues, we can directly see the response of these tissues under that drug stimulation. And we can capture any changes in the force of contraction from these hard muscles, or change in contraction frequency, or even capture any potential arrhythmia originated under drug stimulation. So recently we raised about $7 million to establish a commercial operation in New York, and we'll hire like 2 postdocs as our senior scientists to essentially manufacturing these tissues in-house. And right now we're serving about half a dozen pharmaceutical companies in the US. And our company has this service-based model. Basically, we take drugs from pharma and we run the drug on our devices, and we'll provide the data back to the pharma. And the pharmaceutical company typically also runs animal testing in parallel with testing on a platform like this. So, like I mentioned before, I'm recently started my independent academic career at McMaster University. You can see the research that we do is very much interdisciplinary. Right? We need expertise from stem cell biologists, from clinicians, engineers, or even computer scientists. So we really value people with very diverse backgrounds. So if you are interested in joining us or collaborating with us, or just want to learn more about the research that we do, I encourage you to visit our website. So, thank you very much.